66 million years ago, a rock 10 kilometers wide, the size of Mount Everest, slammed into what is now Mexico's Yucatan Peninsula at 45,000 miles per hour. The impact released more energy than all nuclear weapons ever built, combined, multiplied by 10,000. The sky turned white, then black, for years. 75% of all species on Earth died, including every dinosaur that couldn't fly. One rock, one day. The end of an era. October 19th, 2017. Astronomers in Hawaii spotted something that shouldn't exist. An object moving at 196,000 miles per hour. Cigar-shaped, accelerating without visible exhaust. From another star system. We named it Oumuamua, Hawaiian for messenger from afar arriving first. And we still don't know what it was. September 26th, 2022. For the first time in history, humanity deliberately changed the motion of a celestial object. A spacecraft the size of a vending machine crashed into an asteroid at 14,000 miles per hour, on purpose. The asteroid's orbit changed by 32 minutes. We proved we can defend ourselves. They killed the dinosaurs. They might be from another star. They wander for billions of miles, then streak across our sky for weeks and vanish forever. They're the size of mountains and cities, left over from the solar system's birth, and they remember everything. Meet the cosmic vagabonds. 4.5 billion years ago, the solar system was a disk of gas, dust, and ice orbiting a young star. Particles collided, stuck together, grew. Some became planets: Jupiter, Saturn, Earth. But not everything made it. Millions of chunks, too small to become worlds, too large to disappear, remained, orbiting, waiting. We call them asteroids and comets. But that's underselling what they are. They're time capsules. Asteroids are rocky, metallic. They formed closer to the sun, where temperatures were high enough to prevent ice from condensing. Most orbit in the asteroid belt between Mars and Jupiter, a graveyard of planets that never formed. Comets are icy, formed in the cold outer reaches beyond Neptune. When they approach the sun, ice sublimates, turns directly from solid to gas, creating tails millions of kilometers long. But the distinction isn't as clean as textbooks make it seem. Some asteroids outgas like comets. Some comets have rocky cores. Some objects blur the line entirely. When meteorites, asteroids that fall to Earth, are analyzed in labs, they reveal something extraordinary. Chondrules, millimeter-sized spheres of rock that were molten 4.6 billion years ago, then rapidly cooled in minutes. Flash-frozen droplets from the solar system's violent youth. Some meteorites contain pre-solar grains, dust older than the sun, formed in the atmospheres of dying stars, incorporated into our solar system's raw materials. These objects haven't changed, haven't melted, haven't been cooked by geological processes. They're exactly as they were when the solar system formed, which means studying them is studying the past. Between Mars and Jupiter lies the asteroid belt, a band of rock and metal stretching 200 million kilometers, from 2.2 to 3.2 astronomical units from the Sun. For decades, people imagined it as a dense minefield, spaceships dodging rocks at every turn. Science fiction loved this image. Reality is stranger. The asteroid belt contains between 1 to 2 million objects larger than 1 kilometer across. But if you added them all together, every single asteroid, they'd have less mass than our moon. The belt exists because of what didn't happen. 4.5 billion years ago, material in this region tried to form a planet. Particles collided, stuck together, grew. But Jupiter had formed first, and Jupiter's gravity is brutal. Every time objects in the asteroid belt were on the verge of coalescing into something planet-sized, Jupiter's gravitational tugs pulled them apart, scattered them, prevented accretion. The asteroid belt is a failed planet, a planetary graveyard where Jupiter plays gravedigger. March 6, 2015. NASA's Dawn spacecraft slid into orbit around Ceres, the largest object in the asteroid belt, 945 kilometers across, the only dwarf planet inside Neptune's orbit. And almost immediately, Dawn saw something nobody expected. Bright spots, blazing white against dark gray terrain. More than 300 of them scattered across Ceres' surface. But the brightest cluster was an Occator crater, a 90-kilometer wide basin with a central dome covered in mysterious white material. Scientists stared at the images, trying to understand what they were seeing. As Dawn dropped to lower orbits, eventually just 35 kilometers above the surface, the mystery deepened. The bright material was salt, sodium carbonate, left behind when briny water from a subsurface reservoir percolated upward through fractures and evaporated. Ceres had a subsurface ocean, or used to, maybe still does. The salts were young, formed within the last 2 million years. Some spots showed no darkening from micrometeorite impacts, suggesting they're actively replenished. Ceres isn't dead. It's barely dormant. And then there was the mountain, Oumuamua, rising 4 kilometers above Ceres' surface, taller than Mount Rainier, a solitary dome in an otherwise unremarkable region, flanked by bright streaks that looked like material flowing down its slopes. No one expected a mountain on Ceres, especially one like Oumuamua, said Chris Russell, Dawn's principal investigator. We still do not have a satisfactory model to explain how it formed. The leading hypothesis: cryovolcanism. A volcano, but instead of molten rock, it erupted briny mud and ice. Salt water and slushy material forced up from below, freezing into a dome. Scientists have identified more than 20 other potential cryovolcanoes on Ceres, but they're eroded, barely recognizable. The dwarf planet slowly erases its own features. Oumuamua is the youngest, maybe the last. Dawn proved that even in the asteroid belt, the region we thought was cold, dead, and unchanging, geology persists. Water moves, mountains grow. November 1st, 2018. Dawn ran out of hydrazine fuel and fell silent. It remains in orbit around Ceres, where it will stay for at least 20 years, maybe centuries. An inert monument to our curiosity. January 2nd, 2004. NASA's Stardust spacecraft flew within 236 kilometers of Comet Wild 2, pronounced Wild 2, a 5-kilometer-wide dirty snowball from the Kuiper Belt. Wild 2 spent most of its 4.5 billion-year life in the frozen outer reaches beyond Neptune. But in 1974, it passed too close to Jupiter. The giant planet's gravity grabbed it, flung it inward, shortening its orbit from 43 years to just 6. Wild 2 became a short-period comet, one of Jupiter's captives, now orbiting between Mars and Jupiter. and stardust was there to catch its breath. Stardust carried a sample collector made of aerogel, a substance so light it's 99.8% air with the density of smoke, but strong enough to stop comet dust traveling at 6 kilometers per second without destroying it. The spacecraft flew through Wild 2's coma, the cloud of gas and dust surrounding its nucleus, and collected thousands of microscopic particles in the aerogel. Then it turned around and brought them home. January 15, 2006. The sample capsule parachuted into the Utah desert. Less than a milligram of material. Over 10,000 grains, larger than a micrometer. And when scientists analyzed them, they found something impossible. The grains were hot, not temperature hot, formation hot. Many particles were crystalline silicates, olivine, pyroxene, anorthite, minerals that only form at temperatures above 1,000 Kelvin, some at 1,500 Kelvin or higher. Wild 2 is a comet from the Kuiper Belt, a frozen relic from the solar system's outer edge where temperatures hover around 50 Kelvin, minus 370 degrees Fahrenheit. So why did it contain minerals forged at temperatures hot enough to melt steel? The discovery shattered assumptions about comet formation. Scientists had expected comets to be pristine aggregates of interstellar dust, stardust, the ancient material that predated the solar system, frozen, unchanged relics. Instead, Wild 2 contained a potpourri, high-temperature minerals from the inner solar system mixed with pre-solar grains from interstellar space. Fragments of chondrules, those flash-frozen droplets, sitting next to organic molecules that formed in cold molecular clouds. The comet was a witness to the events that shaped the solar system into what we see today, said Ryan Ogliore, an astrophysicist at Washington University who has studied the samples for years. The only explanation: the early solar system was chaotic, turbulent. Material didn't stay where it formed. High-temperature dust from near the sun was transported outward, possibly by bipolar jets from the young star or by turbulence in the protoplanetary disk. That dust mixed with cold outer disk material and was incorporated into comets forming beyond Neptune. Wild 2 isn't a pristine time capsule from the outer solar system. It's a record of violent mixing, of a solar system in flux, of material traveling billions of kilometers from hot to cold, from inner disk to Kuiper Belt, before being frozen into comets. After 18 years of interrogating this comet, Ogliore said, we have a much better view of the solar system's dynamic formative years. Wild 2 taught us that comets remember not just the outer solar system, but the entire disk. They're archives of chaos. Not all asteroids stay in the belt. Some wander. Nudged by Jupiter's gravity or collisions with other asteroids, they drift into the inner solar system. We call them near-Earth asteroids, objects whose orbits bring them within 1.3 astronomical units of the Sun, close enough to cross Earth's path. We've discovered over 30,000 of them, and we're finding more every week. Most are small, harmless. They burn up in the atmosphere as meteors, shooting stars. But some are larger. A 50-meter asteroid exploded over Siberia in 1908, flattening 2,000 square kilometers of forest. No crater, just an airburst that released 10 to 15 megatons of energy. A 20-meter asteroid exploded over Chelyabinsk, Russia in 2013. The shockwave injured 1,500 people and shattered windows across the city. These are not extinction events. They're reminders. 66 million years ago, a 10-kilometer asteroid struck the Yucatan Peninsula. The impact created a crater 150 kilometers wide and 20 kilometers deep. The initial blast vaporized the asteroid and a chunk of Earth's crust, launching trillions of tons of material into the atmosphere. The sky darkened, global temperatures plummeted, wildfires ignited across continents. 75% of all species died. The dinosaurs, minus birds, were gone. This wasn't cosmic bad luck. It was inevitable. On geological timescales, impacts happen. Which brings us to September 26, 2022. NASA's DART spacecraft, Double Asteroid Redirection Test, had been traveling for 10 months. Its target, Dimorphos, a 170-meter-wide asteroid orbiting a larger companion, Didymos. Neither asteroid posed a threat to Earth. This was a test. DART's mass? 610 kilograms. Dimorphos's estimated mass? 5 billion kilograms. David versus Goliath. DART's camera streamed images back to Earth up to the final second. The asteroid's surface resolved. Boulders, rubble, a loosely bound pile of rock held together by weak gravity. Then, impact. 7:14 p.m. Eastern, 14,000 miles per hour, head on. The Italian companion spacecraft, Chicxulub, captured what happened next. A massive plume of debris erupted from the impact site. Boulders, dust, fragments blasted into space. The recoil from that ejecta acted like a rocket, pushing Dimorphos in the opposite direction. Before impact, Dimorphos orbited Didymos every 11 hours and 55 minutes. After impact, 11 hours and 23 minutes. The orbit shortened by 32 minutes. NASA had defined success as a change of 73 seconds or more. DART exceeded that by more than 25 times. The momentum enhancement factor, beta, ranged between 2.2 and 4.9, depending on Dimorphos's density. The recoil from ejecta transferred significantly more momentum than the spacecraft's impact alone. DART proved kinetic impactor technology works. If we detect an asteroid on a collision course with Earth, we now know we can deflect it, given enough warning time. But DART also revealed something unexpected. Dimorphos is a rubble pile. Low density, weak cohesion, just a collection of boulders barely holding together. The impact not only changed its orbit, it changed its shape. The asteroid is now slightly elongated. Its rotation became more complex, and large boulders ejected during impact carried momentum in unexpected directions, perpendicular to DART's trajectory. This could complicate future deflection missions if we need to precisely control an asteroid's final path. "We succeeded in deflecting an asteroid," said Jessica Farnham, a scientist at the University of Maryland. "But something unknown is at work here. We need to understand the full momentum distribution." ESA's Hera mission will arrive at Dimorphos in late 2026 to measure exactly what DART did. Crater size, mass redistribution, structural changes. We're learning to defend our planet, one asteroid at a time. October 19th, 2017. Astronomer Robert Warwick at the University of Hawaii was analyzing images from the Pan-STARRS telescope when he noticed something moving. Fast. Too fast. The object was traveling at 87 kilometers per second, 196,000 miles per hour, on a hyperbolic trajectory. Not bound to the sun, passing through. For the first time in history, we'd detected an interstellar object, a visitor from another star system. We named it 1I/Oumuamua. The 1I designated it as the first interstellar object ever catalogued. Oumuamua means a messenger from afar arriving first in Hawaiian. But what kind of messenger? NASA's Hubble and Spitzer telescopes tracked Oumuamua as it fled the solar system. Its brightness fluctuated dramatically, suggesting an elongated shape, either cigar-like, 10:1 aspect ratio, or pancake-like. Between 100 and 1,000 meters long, dark red in color, like objects in the outer solar system exposed to cosmic radiation from millions of years. And it was tumbling, rotating end over end every 7 to 8 hours. But then, scientists noticed something strange. Oumuamua was accelerating. Slightly. More than gravity alone could explain. Comets do this. They outgas as the sun heats them, creating rocket-like thrust. But Oumuamua showed no visible coma, no tail, no detectable gas emissions. It accelerated like a comet, but looked like an asteroid. What was it? The theories multiplied. Hypothesis 1. Nitrogen iceberg. A chunk of frozen nitrogen from a Pluto-like world, sublimating invisibly. Proposed by Alan Jackson and Stephen Desch at Arizona State University in 2021, this explained the acceleration without requiring a visible tail. But critics pointed out nitrogen is rare in the universe. There aren't enough Pluto-like worlds to produce the number of interstellar objects we'd expect to see. Hypothesis 2. Hydrogen iceberg. Formed in a cold molecular cloud, Oumuamua might contain frozen hydrogen, solid at just 3 Kelvin. Hydrogen sublimates invisibly and would provide thrust. But later calculations showed hydrogen icebergs can't survive the journey through interstellar space. They'd evaporate in less than 100 million years. Hypothesis 3. Hydrogen outgassing from water ice. Proposed in 2023 by Jennifer Bergner and Daryl Seligman, this theory suggests Oumuamua was a normal water ice comet from another solar system. During its interstellar journey, cosmic rays bombarded the ice, liberating hydrogen from water molecules and trapping it in the ice matrix. As Oumuamua passed the sun, warming slightly, the hydrogen was released, providing thrust without producing a visible coma, because hydrogen is too light to drag dust with it. This theory explains every single weird aspect of Oumuamua, Seligman said. It's exactly what you'd expect an interstellar comet to be. And then there's Hypothesis 4. Artificial origin. Harvard astronomer Avi Loeb proposed that Oumuamua might be a light sail, a thin artificial structure propelled by radiation pressure from the sun. Its unusual shape, lack of outgassing, and acceleration all fit this model. Loeb's hypothesis was widely debunked by other scientists, but he stands by it. We cannot rule out an artificial origin, Loeb wrote. The possibility that Oumuamua is the first evidence of extraterrestrial technology should be taken seriously. The scientific consensus disagrees. Most researchers believe Oumuamua is natural, likely a comet with unusual but explainable properties. We'll never know for certain. Oumuamua is now beyond Neptune's orbit, traveling at 26 kilometers per second. It will leave the solar system entirely and return to interstellar space. In 20,000 years, it might pass near another star. Maybe someone there will detect it. Wonder what it is. Argue about its origin. But here's what we do know. Interstellar objects exist. They visit our solar system. We found one. And according to recent estimates, about 7 interstellar objects pass through the inner solar system every year. We just didn't notice them before. The Vera C. Rubin Observatory, which began operations in late 2025, will survey the entire visible sky every few nights. It's expected to detect dozens of interstellar objects over the next decade. ESA's Comet Interceptor mission, launching in 2029, will wait in orbit for the next interstellar visitor, then intercept it, study it up close, and finally answer the questions Oumuamua left behind. The next messenger is coming, and this time, we'll be ready. The wanderers are everywhere. Asteroids in the belt, comets from the Kuiper belt and Oort cloud, near-Earth objects crossing our path, interstellar visitors passing through. They're small, insignificant compared to planets, but they hold two things planets have lost: memory and threat. Wild 2's dust grains remember the solar system's formation. High-temperature minerals from the inner disk mixed with pre-solar grains from interstellar space. A record of chaos, mixing, and violence that no planet preserves. Planets melt, differentiate, erase their history through geology. Asteroids and comets don't. They've been frozen, chemically, structurally, for 4.5 billion years. Everything we want to know about the solar system's birth is written in these objects. We just have to read it. But they're also threats. The same objects that preserve the past can end the future. 66 million years ago, one asteroid ended the age of dinosaurs. It will happen again. Not if, when. The question is whether we'll see it coming. DART proved we can defend ourselves. If we detect an asteroid decades in advance, we can nudge it, change its orbit by fractions of a percent, make it miss Earth instead of hit. But that requires seeing it first, tracking it, calculating its path. And most near-Earth asteroids, especially the small ones, remain undiscovered. Oumuamua taught us something else. The universe is not empty. Objects wander between stars. Some are natural, comets and asteroids ejected by gravitational interactions with giant planets. Some might be artificial, probes or debris from civilizations we'll never meet. Either way, we're not isolated. The solar system is porous, permeable. Things come in, things go out. We're part of a larger ecosystem. The Chicxulub crater is still there, buried beneath the Yucatan Peninsula, 150 kilometers wide, 20 kilometers deep, a scar from the day the sky fell. You can visit the town of Chicxulub Puerto, walk along the beach. The water is clear, the sand is white. It's beautiful. 66 million years erased the surface evidence, but the crater remains. A reminder that this planet exists at the mercy of rocks wandering through space. We call them asteroids and comets, minor planets, small bodies. But there's nothing minor about them. They're time capsules from the solar system's birth, archives of chaos, witnesses to everything that happened 4.5 billion years ago. And they're existential. One could end us. One already ended the dinosaurs. But we're not dinosaurs. We have telescopes, spacecraft, the ability to see threats coming and, maybe, deflect them. DART proved it's possible. We changed an asteroid's orbit. For the first time, humanity demonstrated we're not helpless. The wanderers are still out there, still wandering. Ceres orbits the Sun every 4.6 years, its cryovolcanoes slowly eroding. Wild 2 returns to the inner solar system every 6 years, losing a bit more ice with each pass. Dimorphos orbits Didymos every 11 hours and 23 minutes, 32 minutes faster than before we hit it. Oumuamua is 10 billion kilometers away now, returning to interstellar space. And somewhere between here and the Oort cloud, the next comet is beginning its billion-mile journey toward the inner solar system. Maybe we'll see it coming. Maybe it'll surprise us, like Oumuamua did. Either way, the wanderers will keep wandering. They've been doing it for 4.5 billion years. We're just starting to pay attention. This is Cosmic Canvas, where we track the wanderers that remember everything and threaten everything. Until next time, look up. The sky is not empty, and what falls from it can change the world. The cosmic vagabonds are out there. Some carry answers. Some carry extinction. And we're finally learning to tell the difference.